that or?
There's no problem. Yeah.
Okay, so we were in the middle of the proof of the theorem, so let me here. And actually, if I'm not wrong, and hopefully you won't find out if I am doing this lecture, there is a much simpler proof that maybe can avoid the ceiling, for example. So you would. So let's leave the hypothesis as they were. And two, the theory of H omega 2 of B, epsilon, zero, and S, and A belonging to UB B. Let's call this T is model complete. And the teaching can come.
Okay, so have to be in some sense definition. This is that every consequence, so that we know this, and then we make these placements. But we have this club which keeps us on the right track.
Okay.
Because then,
and we were trying to go for this direction. So model complete, let me recall, because model complete is a way to assert that this theory is maximizing the family of Phi sentences that are consistent with with the theory of B, let's say, well, with the universal and existential fragment of the theory of B, and it amounts to prove the following. So this is
complete,
for every C x z 25 3, there is theta C of x y 25 3, such that the universal quantification of one is equivalent to the existential quantification of the other. So such that T deduces that for all x exists z C x z is equivalent to for all y delta C x y. So in essence, this model completeness amounts to say all the concepts definable in the language of T are according to T delta 1 properties. So they are all expressible either by a universal formula or by the existential formula. Okay, and so we have started, and we want to show that this theory, in this theory, all concepts are delta 1. So given an existential formula, we must find the equivalent universal formula. And the idea is the following. Find D contained in Emacs. Well, let's be more precise. Find D contained in M, such that for some A M A belongs to Emacs. me, P max is given by the models that satisfy an area 1 is saturated, and the selected ideal is always an S, and this is the selected subset of omega 1. D is universally Berg, and let's say let's call this tau to short. So and h omega 2 tau models exist x exist C x theta, C x theta. So let me change here. Let me do this just for assuming that A is a subset of omega 1, just for simplicity. If and only if it can come for all,
And each one of them
for all M belonging to D, for all J and S further
this is
iteration
a set of countable sets in D.
of
Because
M.
so you can test this exactly the
If
same
the
as
name belonging to M
for this
such that
multiply that you start
J
processing the powers one before
omega
the
1
processing
of
and then one
A
after
is
the
equal
processing,
to
and then
A,
they converge
then
and the same, which is this.
A,
If the Woody kernel is above the course. And okay.
H omega 2 M tau
So now-
in the version of M models exist that you don't have a canonical embedding of CAA as computed in B, CAA as computed in B. So you just know that the two theories agree, but not that you can embed one with the other. So what is the idea? The idea is that I want that these models are very faithful copies of the theory of the universe. They have a they compute the theory essentially they have an elementary embedding of one of B into so that when I iterate those models in the way described by the generic for max forcing, if I'm hitting the parameter for which I want to check the formula, then the truth value of the formula was already decided by the model. Okay? And you see that now this is transforming this existential formula into a universal sentence, because saying, well, this is for all M, for all J and S correct iteration of M, if M in D, this is I'm in D, I have a predicate because I'm saying that this D is universally valid in the code. So I will have a very absolute that one can check it is actually delta 1 in some universally valid set, which is one of the allowed predicates. Okay? So then I have the parameter in M, which is met, and I have, so I have to satisfy these two premises, and they are both without quantifiers, essentially. If I have the parameter in M, which is mapped to the true parameter I want to check, then the formula I'm interested in is already true in this structure. So, and you see this piece. So for all J, so this piece is delta 1. Well, tau M, let's say, So tau is going to be the version of m of this signature. So it will have just
Oh, tau is the
yes.
tau is the
Yes.
structure.
Yes, and what tau? That's yeah. You quote the delicate part, because the problem is that so then exists that, and we need that and let's say b and for so actually I have to put this into the premises. So I'll keep the file. So, okay, that's going. Assume B1, Bk belonging to UB are those appearing in C. So C is the first order formula in this language. It has just finitely many of these predicates appearing, and I assume that they are those ones. So I take those M that are in this special magic set, but also that are correct about this B1 Bk. So correct iteration of M, and M is Bi iterable for all I equal 1k, and here again I'm using that the set of Bi iterable is universally bare in the codes for each I. So this again is coded by the fact that this M is universally bare in some other universally bare set which is not Bi. That is saying I'm coding the set of models that are correctly computing Bi. That version of Bi is the correct version of Bi. And then the conclusion is then M models, sorry, H omega 2 of M and the version of tau of M models exist at C. Sorry, exist at C. E. Okay. And actually, you see here I can reduce, so I can just take the universally best set that I need to iterate. So those B1 Bk. So here I could just put this B1 Bk. Okay, so that I'm sure that in the end I'm correct about this formula, that is the one that I need. Okay, so essentially this is the idea is I have a formula which talks about B1 Bk, and I replace it with a formula which uses as predicate B1, well, B1 Bk and actually not B1 and Bk, but the set coding the iterable models for B1 Bk, and this special set D. That's called is the UB. So I start with a formula which has B1 Bk is universally bare predicates appearing in it, and I use another formula which has those predicates plus those let's say predicates slightly more complicated of this. They have to jump up in the wage order to take the predicate coding the B iterable models from B, and then these other predicates. Okay. And but I still remain in my signature because my signature allows for all. Okay. And so this is what one wants to show. So the idea is, what are the models that are going to fall here? Okay, so this is this special model. Well, the idea is the candidate models, well, they should very much look like this one. So the best option is just to take the collapses of countable transitive models. The problem is that the collapses of the countable transitive models are not in universally bad. So if you take the set of collapses of countable transitive models, are not universally bad. But if they were universally bad, here this would work. Okay? More or less. Well, there is no. I mean, for the specific iteration coming from the anti-collapsing map, this would work. But then there would be other possible iterations, and one has to check. So there are two problems. The first is the natural candidates are countable collapses of countable transitive models. This set of models is not universally bad. And the second is for a specific iteration of those countable transitive models, this condition will be satisfied, but if I move the iteration of the countable transitive model to some other one that is not coming from the anti-collapsing map, do I satisfy again this request? But now I have star. Okay, so that's what I will use star to define this model. So what I say?
When you don't came from the transitive collapse, then it would satisfy for any iteration, right? Because you put it back to M and then any iteration would satisfy.
Well, the iteration, what I mean, if you there is one iteration that is mapping this to A,
Right.
but if you take another iteration that is mapping this to some other, you would still like to maintain that the final model that you end up with is very much faithful to the true H omega 2. So if you take
What are you trying to do? You're trying to show the equivalence.
yes, no, well, what I'm trying to show is to give a universally well definition of this set, first of all. And then also to show, I mean, in principle, if you take a countable transitive model and you take the anti-collapsing map, then and you start with A inside the anti-collapse structure, this big A, then this small a is in the collapse structure, and if you go back, it's going to work. But if you change the iteration of the countable transitive model and you change this A, okay, so if your n is finishing inside this stuff, this type of conclusion should work for any possible iteration of the model. So it will become more transparent as I give the definition. So what I take is I take M belonging to let's say, so let's call this iterable. Such that epsilon model star in B and there is A UP.
From right to left direction.
Yes, yes, from this to there. And there is K from UPM to UPP such that for all J and then correct iteration of M we have that J0 omega 1 of N epsilon delta 0 and A omega 1, let's call it A belongs to M is the substructure, and actually you can even put elementary substructure of H omega 2. Sorry, not H0 omega 1. H omega 2 epsilon delta 0 and then sorry, and here it's I use K. And let me change this letter because it's confusing with the other letter. So P, 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 P. Okay, so and now this looks more plausible that it's universally paired. Still, it is not yet entirely clear that it is. Okay, so what are these? The iterable model, such that there is a very magic map, such that no matter I iterate my model, provided I do it in a net correct way, so I can change the way my model iterates, but those UB sets, I have decided what is their meaning in the final model, and whatever way I iterate, I will always end up in something that mapping this stuff into this. So this is decided the start. This is changing. As I change my iteration, this is changing a lot. But the way this one sits inside here is just you take this, you intersect with m omega 1, and that's it. Okay? And this is, now you see by star, is equivalent to say J is induced by the generic iteration obtained by MA for A belonging to M. Okay. So an NS correct iteration of M is actually the same as the generic iteration induced by the generic filter. Okay. So I have a canonical name for this. So I can replace this. So J NS correct equivalent to J point, canonical name for the generic iteration. Okay. So here I am a bit sloppy. So what this J point will be detected completely by where this A is mapped by the generic filter. Okay. So as I move, so if I fix an A such that this is in Pmax, this generic iteration is detected by this where this A is mapped in the final model. As I move A, I move this generic iteration. If I choose another B inside M, I can get this same iteration using that B. This means this B is mapped to some big B, and as I move the big B, I will. So there is a canonical way to define this object from just. I mean, it's independent of the choice of A. By where this A is mapped by the generic filter. Okay. So as I move. Or you can put them in. Okay, so here it's good because now this is expressible in L of UB. So I'm not anymore quantifying over objects that are not in LOPP, I'm quantifying over objects that are in LOPP. So this universal quantification is fine. And then there is still this, but you see, this is a countable set. And this is a so this map is taking a countable set into the universal Hilbert set. So it is essentially a countable subset of the universal Hilbert set. And by assumption on, for example, theta regular, I have that this object is also in LOPP. Okay? And so I have now that this is a definable set in LOPP, and by stealing, this set is universally valid in the code. Okay, so this is what I'm using stealing actually. So I'm not using it in the part of generic absoluteness, but I'm using it in the part that every set of reals definable in LOPP is universally valid. I use star to transform this concept into this concept, which is expressible in LOPP. So now this formula is fine, except for this parameter, which I have to check that it is in LOPP, and it is because it's a countable set of sets. And then I have now a definition in LOPP, and this definition is giving me something which is universally valid in the course because I have stealing. Okay, so
Where is town used again?
huh?
Where is town used again?
It's used to change this concept into this concept. So if you have M iterable structure, okay, so if M belongs to it and J is NS correct, take A belonging to M such that MA belongs to P max. Then let A equal J0 omega 1 of A, and J is now the generic iteration of M induced by A. So I start with an NS correct iteration, I end up with a generic iteration induced by the generic filter A below the condition.
Generally, you mean the max generic?
Yes. Yes. By
I thought this is.
yes. B max. B max.
Okay.
Okay. And conversely, if I have a B max generic iteration, it is also NS correct. Okay. So the star is used to transform this concept into something expressible in LOPP. So that it is forced by P max in LOPP. Okay, so now I have a definition in LOPP, and it's almost self-evident that this definition will work. So let me.
Yeah, I want to ask a little bit before you. So up. You say here, find PUB, subset of that, PUB universe spirit. So when there's some confusion in my mind when I first, I mean, why would be, what's the problem in finding, but if finding like, take the empty set or something?
Yes.
Now here you.
So not only it is I find it, but essentially you can almost automatic by its definition that the collapse of a countable model will end up in this set.
So what you're saying here is that we will find,
Yes.
yes, okay.
So a very large set of, I mean, dense and such that if you intersect it with every with a set of iterable models for some universal set B, it is still dense. Okay. And so back if B belongs to UB and M substructure of H gamma, or let's call it N. Countable with B and D, well, D, in M, then in N, then N it's collapse, it's collapse of N is in DUT and is big iterable. As weakness, by J M restriction UB M to UB. J
So
M
first,
is inverse of the
so we can,
of the
now rather than saying that for all but finitely many, something happens.
Okay, so this is the key observation. So you take a countable substructure of H gamma, which has some universally diverse set inside. You collapse this structure. Well, the fact that it is B iterable is a standard fact of it's proved in Larson test, more or less. And then we have to check that it is in the UP. Right?
What is the
This set. So what happens is that so we have that Jm goes from M to H gamma and induces bar J iteration of M, J alpha beta M alpha 2 M beta alpha less or equal beta less or equal omega 1 which is given by essentially using the self-generic filter. This is what I said the other time. So here you go from M to M equal to 0. You go to M1, which is equal to F of M intersection omega 1, F belonging to M, and then you go to further, I mean, it's the better notation. N, which is equal to N0, and here is N intersection omega 1, F belonging to M, then it goes to N2, and it ends up in N omega 1, which is the substructure of H gamma, and here you have Jm and pi m, that is M 0, M, and then you go to M1, which is equal to F 0, F belonging to M0. What is G0? zero equal S such that Jm such that omega 1 of M, which is equal to N intersection the two omega 1 belongs to J and S. And here the map is sending F map to J M JMF in evaluated in N intersection omega 1. And so on and so forth. You can follow this iteration here, and you can pull up following this rule, and you end up here with M omega 1. And following this rule, you get a full elementary embedding of M omega 1 into each term. Okay? Now I'm not interested in the full elementary embedding of M omega 1, I'm just interested in the piece of elementary embedding of H omega 2. Okay? And so and the piece given by H omega 2 is completely determined by the iteration. I mean, if you look, this model contains the true omega 1. So the map defined here, the first orbital move is the omega 2 of this model, which is an ordinal below the true omega 2, and it is so the map is the identity on the H omega 2 of this model. Okay, so I have that this map is the identity on the H omega 2 of the model, and the unique things that it moves are the predicates. So it's moving this predicate to the true non-stationary predicate, and those predicates by some rule. Okay, but I'm not interested in the bull predicates that appear here. This may be complicated to control. I'm just interested in this small piece, which is decided at the start. This small, I mean the pointwise image of the predicates given by it. So, and this is decided at the start, and I have no problem. Okay. So what I do now, I check what is true. I mean this. So I have this J. So pick A belonging to N. Check let A equal J0 omega 1 of A. Then J is induced. Is the iteration of M induced by A. So what I get essentially is that MA forces that the generic iteration J is such that H omega 2 of M0 omega 1 epsilon delta 0 NS M omega 1 J0 omega 1 A for A which belongs to UB of M is elementary in H omega 2 of L of UP GA epsilon delta 0 NS, and then I have K A, sorry, my K is KM.
You said you can avoid ceiling.
You
don't need to know that D is.
Huh?
You don't need to know that D is inversely there.
What?
You said you can avoid ceiling.
Well, I can avoid the part of stealing about generic invariance. B belonging to B.
you're right, energy road will go on.
Yes, a moment. Okay, so what happens is in the generic filter induced by this A, this statement is true, and the forcing is homogeneous, so it does not really depend on the generic iteration induced by this A of M, but I can just flip the iteration and this statement will remain true, because you see the unique parameters are these and these. This belongs to LUB. And this is moved canonically by the homomorphism that moves a generic filter to the other generic filter. Okay. So I mean, here I'm a bit. So what happens is I have this object detects a generic filter for Pmax. Okay. The statement is true in the generic filter detected by this object, so there is a condition in that generic filter which forces the statement. This condition is also in the generic filter, and one can use the homogeneity of Pmax to argue that actually it is this condition that forces the statement. Because if not, you would have some other condition defined in this one, which forces the negation of the statement, but then the homogeneity of Pmax would give a contradiction. Because this parameter is moved by the homomorphism, automorphism, which maps the condition that decides for the truth to the condition that decides for the falsity. This one is not moved, it's the same. Okay, and so we get that this set is universally valid. So this set is universally valid by its definition. But it's large because of this fact. If you take the countable transitive, the collapse of a countable transitive model, you end up in the fact. Okay? And well, now it's easy to check that this condition will be satisfied. So, can I erase this piece? So it's clear. So what happens? Suppose that this statement is true. So H omega 2 B1 BK mod of X is Z C K Z. Well, what is the so what happens? Take M as a ball. Take, first of all, there is an M which satisfies the premises of this. I mean, there is this quantification is non-empty. Take a countable substructure of H gamma, collapse it down, and check that the generic iteration, the iteration of that structure induced by the anti-collapsing map is witnessing this fact. Okay. Now take some MA such that there exists J iteration of M mapping A to A. Well, and then we have that by definition of this set, we have that M omega 1 epsilon delta 0 ns M omega 1 B1 BK. I just interested in this one, so B1 BK M omega 1. This is fully elementary in elementary in H omega 2 ms epsilon delta 0, and here I have the KB1, sorry, yeah, KB1, KB, sorry, B1, why it is so? Because text MA, if MA is in this set, it has this magic mark K. There is K from M, well, from the universal reverse set of M into the universal reverse set of B, such that essentially it is saying I am B iterable for all the sets which are in the image of this K. Okay? Whatever iteration I take of myself, if I take a set in the image of K, I'm B iterable for that set. In particularly for this B1 BK that I put inside my M. Okay, and so since I have full elementarity and my statement was true here, it has to be true here. Okay, so I have shown that if I have a statement which is sigma 1 statement which is true here, then whatever M small a and j I take, provided this condition is satisfied and my M is iterable for all the predicates appearing in the formula, then I will get that H omega 2 of M will satisfy the extension factor. And conversely, if I have this statement true, well, it is clear that this is also, this is much easier. Okay, so this is proving the theory. And am I out of time? Or? I have 15 minutes.
Okay, you don't have to use.
Is it fine? Do you have questions so far on this?
The other direction is
The other direction is, suppose that this holds.
no, not that direction, the theorem direction.
This one. Yes, you're right. So I can use the other thing. So I can now take advantage of the Asper-Schindler result for the other direction, and I will use the super compact. So assume so T complete. Well, we have seen that this means this implies T, and let's call theory of B, T of B epsilon delta 0, NS A, B. Let's call this S. We have that T is equal, sorry, let's put it here. The models of T are exactly the S is M, such that M is S existentially closed. Okay. Because my assumption is that this theory is the model companion of this theory, and this holds exactly when you have this equality. Okay. And what does it mean in particular? It means that whenever I have a superstructure of M, which is a model of the universal theory, then M is sigma 1 elementary in that term. Okay? So what I prove, I don't prove star, I prove so equation omega 2 epsilon delta 0 ns a no it's b belonging to b of t is sigma 1 elementary in Vg epsilon delta 0 ns Vg Bg b belonging to b of t if G is V generic for NSSP force. Okay, so that's the main advantage of accuracy inverse. So they show that from these you can get star. This is apparently much weaker than okay, but then now it's quite straightforward. Can I raise this board?
For what, G is generic for what kind of process? For C? For any? For any or?
No, for any SSP force.
Okay.
So if you take an so essentially it is BMM but plus plus and also the universal legal predicate. So this is it's easy to see that this is it. Well, let's say essentially the same proof that gives you BMM. If you check that proof and you have a predicate for an S, gives you BMM plus plus, and since the universally bare are absolute and cross generic extension, it gives you also. But the difficult part is to prove that this is the same as star. Again, this direction is not difficult. The problem is this direction.
So in the Anderson paper, they actually use this.
Huh?
The Anderson
But they prove that this implies this.
Yeah.
That's what it is.
Only without all, I don't think they put all.
Well, they put all. They use the fact that they say if I have a class of universally bare set which is projective, which means that it's closed under complementation, intersection, projection, and generically, I don't think they use that it's generically bare.
You have for each individual you miss out on one problem.
Huh?
If you have the statement for each individual.
Yes, yes. So they prove that for each individual UV set they can get the state. But the problem is that this is, I guess that if you want to formulate it like, well,
Each formula you're trying to work by finding many disciplines.
huh? Yes, yes. But you need you need a proper class of Putin in order that you know that it's cloned under projection complementation. And essentially that they find. Okay, so now this task is not hard because so we just have to show that if our theory is model complete, so if this theory is model complete, then we have that whenever a generic, we take a generic filter for an SSP portion, and we have a sigma 1 fact proof here, it reflects. Okay, because then we will get that this model, B satisfies this axiom, and then we will get star. Okay, so let's exist x, c, x, a, b such that for some SSP forcing, BG model exist x, c, And then we have, what happens is now that h omega 2 epsilon delta 0 ns a belonging to UB is the substructure of BG epsilon delta 0 ns a belonging to UB, and the universal theory of this structure is the same as the universal theory of B by the theorem I gave the other day. Okay? And exercise M is S EC if and only if it is S for all. So you don't have really to get a full model of the theory S. It is enough that you get a model of the universal fragment, and why? Because we have this lemma that says that if you have two models that have the same universal theory, you can. So if you have two theories which share the universal fragment, every model of one theory can be extended to a model of the other. So if you have that, you have a model of this theory which is a superstructure of this one. You enlarge this to a bigger model, which is a full model of the theory of this, and now you reflect. Okay? And so what happens is that this is a model of S for all. The sigma 1 statement is true here. This is S existentially closed because by assumption. Okay. Okay, and then we get that, so this, let's call this M. So M model existence, CXA, because it is S essentially closed, and this is the model of S for all, and satisfy the okay, and so we get the other implication.